Okay, so we'll start up with our sixth lecture here on Physics 1. So we've gone through quite a bit so far. Units, one-directional motion, what vectors are, two-dimensional motion, forces, how we can get things to push or pull, and equilibriums, and there's just actually a lot to unpack there. We've gone a long ways so far. The next step on this is to apply these laws to other things. So we've got a little bit more extra to work on for forces. There's a couple of other aspects that we're going to look at here. Okay, so let's start in on that. We want to get back to circular motion. We had talked a little bit about circular motion already, and you got a couple of equations for it, and we just want to touch base in here and see how forces react with that circular motion. So if we remember back for our definition for uniform circular motion, it was described as having something traveling in a circle at a constant speed, right? But there's a weird part of that that you probably should have questioned back then. If it's at a constant speed, how does it have an acceleration? There had to be a centripetal acceleration, and how did we get that acceleration if it was a constant speed? The definition of acceleration, of course, would be change in velocity over change in time. So this centripetal acceleration is a little bit different than a traditional acceleration, and if it has an acceleration, we can turn it into a force. So as long as there's an A, you slap an M on it, some mass that's swinging in a circle, and you'll end up with a force. And we call that a centripetal force. Okay. It's written down there. You can see your formula for it. It's the one of the few new equations I'm going to throw at you in this chapter. But why does it exist? And the thing is to just not believe everything you're told. It's not a real force. They call it the fictitious force. The reason that there's an acceleration to it is that your speed is not changing. That's correct. You have a constant speed while you're going around in a circle. But your velocity actually is changing. Not its magnitude, but its direction. The direction of the velocity changes, and then that's what's leading to this accelerative force that we feel. Centripetal meaning center seeking, so everything points, you always feel this force pointing towards the center of the circle. And when I say it's not a real force, higher level physics, if you do go into upper levels and you are curious or you have a class on it, you'll see that it doesn't follow other certain laws, and it ends up kind of dropping out of higher level equations like Lagrangians and Hamiltonians and other things that deal with classical mechanics. So that's well beyond the scope of this class. So we're going to use it to help solve things. We can obviously use this to help with a couple of other questions, and we can have solutions that make sense to us on this, and things that we can observe in real life, even though we're giving it this fictitious name of calling it a force. We can still treat it like a force and have it solve some of our problems. I know some students struggle with that, well, if it isn't right, why are we learning it? Or if it's not real, why do we care? And you might think that's a little bit absurd, and that's totally fine. If you do kind of feel that way, stay away from mathematic courses that deal with complex numbers, because that's really going to have you rip your hair out. It is just because something falls out of equations later and it was misclassified or misinterpreted in an intro level doesn't mean that we can't use it. All right, so complex numbers is a great topic too. If you do have more curiosity about that, you'll learn all about imaginary numbers and how we use those to solve all sorts of problems. And that right in the name tells you it's an imaginary number, so it's quite something. All right, well, moving on anyway. We have this new force, this centripetal force. If there is an A attached, we can slap an M on it and come up with a new force, and we're going to call that the centripetal force. And it's just the A that we used for centripetal uniform circular motion, which is the V squared over R. We put an M on it, and we have mv squared over R. And we can use that. We can set problems up just like we did with the other forces and use that equation to solve for some various things. So we'll do a few examples on that. And then the rest of this chapter is on resistive forces. Okay, so these are just another variation of forces. This isn't circular motion or anything, but it is something that we haven't talked about yet. This one, of course, is real. Don't worry about that. You can kind of think of a resistive force as a kind of a different type of friction. We've neglected air resistance and minor things like that, like flow and drag, and we've kind of ignored all that up until this point to make the math a little bit easier. But those things are out there; they exist. So you can obviously see those. And so for small velocities, small scale speeds, we have an equation that it follows, and we call that the resistive force. So you can think of it like friction. It's resistive. It works against the motion. And it occurs when an object moves through a liquid or a gas. Okay. So the equation is as follows. You have capital R as resistive. And that is equal to, and then because this is in a vector form and it works against you like friction, we've added a negative sign so that it maths. This lowercase b term, it's a constant value, but it's problem specific. It depends on the properties of the object, the gas or liquid that you're going through, all these little variables and changes, they all get combined into one constant term for us that we call b in this case, the lowercase b. It is, of course, proportional to the velocity. Okay, so we do have a velocity in there. It's one of the only forces that is proportional to velocity instead of acceleration, which means that we can now achieve something that we call terminal velocity. It's where these two forces cancel. It's the force of whatever is pushing on it, and then the resistive force pushing back end up matching up and canceling. And if the two forces cancel, you know that it moves with a constant velocity. So we can see a little bit of an example here where we have perhaps this ball or whatever this is here, this particle. If we started off with some velocity 0, right, so it's at rest, and we just decide to drop it, to put it into free fall. By now we should know that when an object is in free fall, the acceleration is 9.8 in the downward direction. So we let the ball go, the ball starts falling, and without this resistive force, it would continue to speed up over and over endlessly. It would continue to speed because there'd always be that acceleration, always bumping the speed up faster and faster and faster. But because there's a resistive force now that pushes back on it, proportional with speed, the faster it goes, the harder the resistance pushes. Okay? And eventually they're going to balance, they're going to match out. And at that time, you can then see that the velocity, the red arrows here, the velocity eventually becomes constant. That velocity is known as the terminal velocity. It is the fastest an object can fall through that medium. It's a terminal velocity. It can't go any faster. At that point, of course, the acceleration is 0 because the two forces have canceled each other. The overall acceleration is 0. This is in air or gas. If you look at it in a liquid, I think it's a little bit easier to identify because we can draw out a free body diagram and have the force of gravity pulling down, resistive force pulling it back the opposite way of the velocity, and then we can see velocity here in red as it's coming down. So this would be the difference between dropping a bowling ball through the air or dropping a bowling ball through water, through a pool. They will fall with different velocities because they're in different mediums. If we're looking for terminal velocity, if we need to solve for that for some reason in some of our questions, we can use the fact that it's in equilibrium. If the total acceleration is 0, we can set up the sum of all forces to be 0, and there's only these two forces that are acting on it, which means these two must equal each other. So we would have the resistance force, which is negative BV, is equal to mg. And we would be solving for the velocity at that point, because the velocity then would be the terminal velocity, which means you just have to divide b over to the other side. Okay? And if you do that, you come up with this equation down here. Right, this is where the two forces cancel, and you end up with a terminal velocity of mg over b. Okay? Sorry, apologies. My email apparently is going crazy right now. Which is great for slow motion stuff. All right, so this is something falling through the water or through a dense gas, anything with a slow motion. And we'll have a couple of questions on terminal velocity of something that is going slow. You'll know that it's going slow if it gives you a b term. That means then we're already in the slower, or it might state specifically that we're traveling at a slow speed. If we're traveling at a fast speed, there is another variation. For fast motion, we find that the resistive forces are better estimated to be proportional to the velocity squared, because v squared would exponentially increase that resistive force. So we have a different model, and there's a couple other variables that we've thrown into the fast model because more things play a part. First off, we have that this resistive force here, now it's not in vector form, so we're negating the minus sign here, but remember that resistive forces are always going to work against the motion. It's just equal to 1/2, and then multiplied by this capital D term, and the capital D term is what is known as the drag coefficient. In a lot of ways, it takes place of the B term in the slower model for the resistive forces. And this is always what companies are trying to reduce to make cars get better gas mileage, or rockets to go into space. The smaller the drag coefficient, the less the resistive force, and the higher speeds things can reach. So that's the drag coefficient is what that's known as, is the capital D. This weird looking P thing next to it, this is actually a Greek letter rho. Rho stands for density in a lot of cases with a lot of different subjects as well. You usually see rho as density. This is the density of the material the object has to pass through, so it depends on if it's an atmosphere, or if it's water, or if it's the a lunar lake of some extra planet that we're discovering or something. Anyway, it's the density of the material that the object needs to pass through. The capital A behind that is the cross-sectional area of the object. So if you can make things smaller and they'll pass through things easier. If you can make them pointy, you'll have a lower drag coefficient, and all of this leads to a lower resistive force. If you, example of this, let's say a frisbee type kind of thing, right? If you throw a frisbee and it travels through the air in the horizontal direction, you would have a very small cross-sectional area. You're only seeing the lip of the frisbee as it glides through the air, and you'll notice that it glides through the air much easier this way than as the circle, putting the face and trying to shove the face through the air. So cross-sectional area, of course, matters in this. This is why a lot of our vehicles, especially sport vehicles, have a lot of curves and are small and sleek, because they want to keep that surface area to a minimum compared to a Greyhound bus, which is has one job of hauling people. So it has a large cross-sectional area in the front. Okay. And I think you get that anyway. And then, of course, the V just stands for the velocity. Okay, whatever the velocity is that you're traveling at. So a lot of constants, and then V is our velocity term, which could be changing. Working the same way, you can also get a terminal velocity for fast-moving objects. You just find out when the velocity reaches its terminal velocity. The acceleration goes to 0. It's a resistive force. You'll set it up the exact same way as you did the other. Make the sum of the forces 0. Compare the force of gravity with the resistive force. This one gets a little bit trickier because you're going to have to get rid of the square, which means at the end there'll be a square root going in. There's a factor of 2 because of this half. And then you have a big constant here on the bottom of drag times rho times area. But we can do that for that as well. This is terminal velocity for fast-moving objects. This would be like skydiving, race cars, rocket ships, those kind of things. Skydiving especially, in that it's for MG. In free fall, if you were doing this for a race car, it would be some extra formula stuff going in there that you'd have to take into account. But terminal velocity for fast falling objects. We might look at a couple of different objects in this one. We'll do a couple of examples of objects that reach terminal velocity based on their masses and the cross-sectional areas and stuff. So a famous one for this one is dropping a coin off of a very tall building. If we didn't have these drag coefficients, that object would continue to accelerate and cause damage when it hit the ground. But because of terminal velocity, we don't have that issue. It's actually a fun one with rain as well. If we didn't have the atmosphere that we have to slow the rain down with a resistive force, a rainstorm would be absolute chaos for humans and all sorts of animals, rather than a nice, delightful shower out there. So it's kind of interesting. It's got some interesting stuff, and that's why we're glad to have it. And terminal velocity is kind of fun to play around with and come up with some scenarios to give examples on. All right, anyway, we will head on over and do some examples of all of that. It's a little bit of a shorter chapter because the last chapter had quite a bit of problems. So anyway, let's head on over.
Yes, we'll start with some examples here on chapter 6. First one I want to get into is centripetal force. So we have the equation F subscript C for centripetal force is equal to m times the centripetal acceleration, v squared over r. When we deal with the centripetal force problems, remember that centripetal force is not a real force, fictitious force. It's in an accelerating frame. And as such, we can't really give it a direction. It's center seeking is what centripetal does mean. But when we do our problems, when we think about how we want to set things up, I do find it easier to just place the centripetal force as the overall acting force, the sum of all the forces, because in centripetal problems like this, it's going to be the only acceleration that we have. Anyway, I'll show you what I mean as we do this example. So example 1, starting off, we're going to have some object with some mass of 0.5 kilograms. It's attached to a 1.5 meter long string, and it states that that string can only withstand 50 newtons of force before it breaks. Now, assume the object spins horizontally on a table. What is the fastest it could spin without breaking? So it gives you a lot of information here. We can kind of draw this one out. If we look at it from an up-top view, we'd have whatever this object is. We'd have a 1.5 meter long string that's attached to it. And then the object spins horizontally. Now, gravity doesn't play a part. That's why they put it as spinning horizontally on a table, so that we don't have gravity taking hold of this. Now, like in all force problems, you would draw out a free body diagram, right? So we have this object here. It doesn't state where the object is on the circle, so but we know that there's going to be some tension in that string. So if we have tension would be pulling this thing back. keeping it in line so it doesn't go flying off into space. That would be the tension in the string. Now, force of gravity doesn't affect anything. It's spinning. It doesn't say anything about friction. It doesn't do anything else. We do not put in the centripetal force, but we do know that the centripetal force is center seeking. So these two forces are actually pointing in the same direction currently. Okay? But I don't list it on my table. That's the point I'm getting at. I don't list it on the table. Instead, I want to sum up all my forces. Okay? And if I summed up all my forces, the only force that I see in there is tension. Now, the mass, whatever this is, I just drew it here at the top. That happens to be the tension going down. If I would have drawn the box down here at the bottom, then the tension would have been going up. Same left, right, or any angle inside of here. So we just want to leave things broad, leave things open. That the sum of the forces here is just equal to tension. Okay, because it doesn't state where it is on that string at all. And in fact, it won't change our answer for the most part, because all we're doing is looking for a velocity or a speed. Okay. So what is the sum of the forces? I look at it and I go, okay, there's centripetal force that's occurring. That's what's causing all of this motion to take place. That's the acceleration. It's the only acceleration that's in our problem. So for here, I will put down that that's just equal to the centripetal force. Okay, so what I'm doing, I shouldn't probably put it like that. I should do it the normal way. Let me try that again. For the sum of all the forces, that's what I'm going to put for the centripetal force. We'll have Fc is equal to T. And then what is Fc? Okay, well, Fc is equal here to mv squared over r. And what is tension going to be equal to in this case? Well, it says it can hold a maximum of 50 newtons, and we want to know how fast can it spin without breaking. So we want to put that tension at the maximum, right? It's the tension in the string. So we want this tension to be at 50 newtons so that we can find the velocity that takes place at 50 newtons. Okay. So then we just start plugging in the rest of our information. The mass that we got is going to be 0.5. V squared is what we're looking for. We're going to divide that by the radius. The radius was 1.5. Oops, and this is equal to 50. All right, now we're going to do a little bit of math on that. Multiply by 1.5 on both sides. We're then going to divide by a half, or you can do the math any other way that you would like. Finally, we're going to have to take a square root of our answer. And at this point, I'm going to kind of skip some of the math. I'm assuming that you do know how to do some of this simple mathematics now. It's just algebra. Nothing wrong with a little algebra in there. So, and if we do it all out, we should get a velocity. Do it out on your own. Plug it in your calculator. Figure out what you're going to get for your velocity. And we should get something around 12.2. Yeah, we solve out for v, we should get something around 12.2. And, 12.2 meters per second, that's a reasonable answer. I think we've done enough problems here to realize what velocities are kind of reasonable for things. You are spinning it around pretty quickly, but you're not, going as fast as a speeding bullet or something like that. And what that means here is that that's the maximum velocity. So 12.2 meters per second. If anything is over that speed, the string breaks, because now you're applying more than 50 newtons of tension. Anything under that speed is fine. The string remains intact. Okay, so that's the maximum speed. You'll get a couple of these questions in homeworks and stuff as well to show how to do those. Okay. All right, we'll move on to another one. Okay, so here we have our second example. In this one, now we have a 1,500 kilogram car. It's moving on a flat horizontal road. There's a curve in the road with a radius of 35 meters. There's friction involved in this one. There's a coefficient of friction of 0.523. And it wants to know what is the fastest speed the car can take the curve without losing control. Okay. So again, I'm just going to draw. Let's see, I'll go here and I'll kind of draw what's happening. So we've got a car coming down the road. Aerial view of the car coming up the road. This radius here is our 35-meter radius. Okay. And the car is going to take that curve. So if there wasn't friction between the tires of the car and the road, the car would slide off the road. It would go straight on forward. So we know that there's friction involved. It tells us there's friction involved as the car goes around. It also tells us that this is a flat horizontal road, so that there's no banking to the curve, or it's not on a hill where it's going to have some extra gravity thrown in that direction or anything. And it wants to know what is the fastest speed the car can take. So it tells us then that it'll be going across with a constant speed. Okay, so this is kind of what's happening. We get that a little bit. Now, if we want, we'll draw out our free body diagram of the car. There's our wonderful boxcar. And what forces take place on this car as it travels around that curve? Okay. This is the, maybe it's a Cybertruck. This is the back of the car. Or maybe it's the front of the car. It doesn't matter. I'd call it the back. Anyway. Well, with every object, right? It's on the road. It's driving around. So, which means we're going to have the force of gravity. Luckily, we know that that's just m times g. If there's that and it's on the road, that means there's going to be a normal force. Right? The road's got to push back on the car. What else do we have going on? Well, there's friction involved. And I'm going to say that it's going around the curve, which means friction is going to have to point towards the center. Friction force. Why does the friction point towards the center? Okay. The car wants to skid off. Still in my car? I don't have the car anymore. The car wants to slide off the road. It wants to continue straight. So the friction is pointing the inside direction. The friction on the tires. The tires want to go this way. Friction is pulling it this way so that it stays in that equilibrium as it makes its way around. Okay, so we have some friction force on the tires of the car, keeping it on the road. So our free body diagram looks something like this. Okay. Now, we don't put in our centripetal force. Instead, we're going to write out our equations. Okay. We look at the sum of the forces. So I need the sum of the force in the x direction. I need the sum of the force in the y direction. So what's happening in the x direction? Simply the friction force, right? So the friction force is mu times the normal force. Yeah. What's happening in the y direction? Well, I have the normal force pointing up, and I have Fg pointing down. Okay. What else is happening here? If I have the sum of the forces in the y, it's asking, is there any acceleration in the y? Is the car jumping up and down at all in the y direction? The answer to that is no. It said it was a horizontal road on purpose. So I can take my sum of the forces in the y direction and I can make them zero because there is no sum. There is no acceleration there. It overall cancels. It goes to zero. Okay. That tells me that Fn then, if I move Fg to the other side, is equal to Fg, which is equal to mg. So both those forces are the same. They'll cancel out. And we've done several problems like that already. So that takes care of the y. What about the x? What are we looking for? We're looking for speed. And so far, I don't have anything to do with speed yet. So what is happening in the x here? Is there an acceleration in the x? Well, there must be something to counter this, right? There must be something that counters the frictional force. So yes, there is an overall force in the x direction. And it is hidden in that it is going around a circle. So the friction force of the tires pulling in towards the center of the circle, center seeking. This then is going to be my mass times velocity squared over r. That's my centripetal force. That's the overall sum. mv squared over r. And they're both in the same direction. I'm just going to leave them both as positive. Because again, it doesn't state if the curve went the other way in the road, and it's tough to kind of do those things for direction-wise. So these are both pointing in the same direction regardless as it goes around the circle, no matter which way the curve is in the road, they both point in the same direction. Okay. There I've got my velocity. That means that's what I need to solve for then, right? Mass, given in the problem. I have my mass, so that's not an issue. The radius, given in the problem. Okay, so this is looking pretty good. Mu, that was given in the problem. And the normal force I can solve by using this property of the y direction forces, right? I know that the normal force is equal to m times g. And again, I know mass and I have gravity. So everything here should be solvable. If we take and we start writing these things out, okay, we'll have 1500 for our mass. We have a v squared. The radius of the road is 35. Okay. That would be equal then to, so I'm just writing this top equation, plugging in everything I know. The coefficient of friction, 0.523, times the normal force. And the normal force, I'm going to plug in mg. Okay, so we end up with something like that. Now this is kind of interesting. We have 1500 on both sides, so that actually just cancels out. So it doesn't even matter if this is a small car, if it's a large car, if it's a motorcycle, or if it's a semi. Mass of it doesn't matter at all. This is actually how they determine what the speed limits are for these curves in roads that you'll see when you go driving, in a curvy environment. You'll see that certain curves have different speed limits. This is how they figure it out, and it works for every single vehicle because the masses end up canceling away anyway. All right, so now all we got to do is solve for v squared, which means I'm just going to take everything that I have there, put it underneath a square root symbol, and then multiply it through. So I'm going to have 5.23 times 9.8 times 35, all underneath of a square root. And I get a velocity. Hopefully you're putting that into your own calculator, determining what it should be. And we get something around 13.4. Of course, remember the units, meters per second. Box the answer when you're all done. Get used to those habits. They'll help you out in this course and probably other courses as well, if there is something that is nice and defined as your answer. All right, 13.4 meters per second. Is that an okay speed? Yeah, I think so. It's not a very fast speed, but 35 meters isn't a very big radius, so it's probably a pretty tight corner that you're going around. I think that one just works out okay. Okay, on to another one. Okay, let's look at another one. Example 3. This one's more of a pictorial. I've got a Ferris wheel here that is traveling around. It's got these 4 baskets on it, and it travels around this way with a constant velocity. Now, inside one of the carts, we have a passenger. Maybe it's loaded up with cats or something. Okay, and it travels its way around the Ferris wheel at a constant speed. Mass of each of the riders, cart, critters, people, whatever, are 100 kilograms. The Ferris wheel spins with a constant velocity of 4 meters per second, and the radius of the Ferris wheel is 20 meters. So this one has two questions. It said, what is the normal force at the bottom? Okay, so when the cat here is at the bottom, what is the normal force that is being applied upward to keep the Ferris wheel cart and passengers and everything seated? And then what is the normal force at the top? Okay. Is it going to be different? Have you ridden enough Ferris wheels? I don't know. So we're going to draw a free body diagram. Here's our cart. Okay, our cat inside, all happy that it's not being cooped up. What are the forces that are acting on this cat? Or rider, or whatever you want. Well, there's the gravity force. That's always occurring, right? And that's always just equal to mg. It's always pointing down. And then there's the normal force, keeping the cat up. Now, initially, when you start this problem, you might get stuck and go, well, those two are going to cancel each other out. They're going to be the same because there's nothing else going on. Right? So the normal force is the same at the top and the bottom. It's just mg. Well, not quite, because we have something that's moving in a circle. We do need to continue on the problem. What do we normally do here? We start with our sums of our forces. Is there anything happening in the x? Sum of the forces in the x is 0. There's no forces occurring in the x. So I don't even need to write that. There's nothing happening. It's all happening in the y. Okay. Some of the forces in the y direction would be the normal force pointing up and the gravitational force pointing down. So I'm going to put a minus mg because that would be down fg, minus fg, or minus mg for the mass times gravity. All right, what is happening in the y direction? Because it's going in a circle, there's going to be some centripetal force. All right, so we got to take a peek and see at what point are these together and at what point are these different. Okay, so when they're at the bottom, when this is at the bottom, what direction is the normal force pointing? Well, the normal force is pointing up, right? It's traveling towards the center of the circle, right? It is center seeking. So at the bottom, we will have centripetal, the centripetal force here. Okay? So let's look at that. At bottom, I will have mv squared over r is equal then to the normal force minus mg. Okay. We can then plug in whatever we need for our masses. So here we would have 100. The velocity is 4. The radius is 20. And that would then be equal to, well, let's see, let's do a little bit more algebra. We can do this. Okay. A little bit more algebra. Let's move that mg to the other side. So we'd have plus 100 times 9.8. And then this is equal then to the normal force. So you see, I just added mg to the other side of this equation. So we've got this plus mg is equal to the normal force. All right, let's plug that into our calculators, see what we end up getting. We've got 100 times 4 squared, which is 16 divided by 20. This gives us 80 here. Sorry, not the whole problem. This gives us 80 plus, of course, 100 times 9.8 gives us our 980. And that's equal then to whatever the normal force is. Okay, which would be 900 in this case, or would be 90 plus 80. Okay, 1060. Okay, so at the bottom, it is 1060. Okay, and of course, newtons. Okay, now let's take a look at the top. Okay, what happens when we get to the top? I'm still going to have the sum of the forces, which is going to have to be the centripetal force. So I'm going to have an mv squared over r. I still have the normal force pointing up, right? And I have gravitational force pointing down, but that's going to give me the exact same answer. There's a little tiny difference here, right? At the top, when the cart is up here at the top, what direction is the normal force pointing? It's pointing up. Which direction is the centripetal force pointing? It's now pointing down. Okay, so there's a change there. They're no longer aligned. These two were pointed in the same direction. At the bottom, they both point towards center seeking. At the top now, those two vectors, those two points are now opposite. It's no longer center seeking. It wants to push you up and off of the ride, which means it doesn't change the direction of the normal force. It doesn't change the direction of gravitational force. It does change the direction of that centripetal force, being that it's now pointing downward towards the center of the circle. So that gets a negative in there. Okay, now we've already done these calculations. mv squared over r is 80, but now it's minus. So we're going to end up with a negative 80 is equal to Fn, and then mg is still 980. Okay, if we bring that over to the other side, we'll have negative 80 plus 980, and now the normal force is what? Now it's only 900 newtons. Okay, the negative sign really changes the problem up. So at the top, it's 900 newtons. Okay. So there's a third part of this problem as well. It says, what happens if the ride malfunctions and we get a velocity of 14 meters per second? What is the normal force then? Okay. So this one here, I'm just going to, I'll write it over here in the corner, I guess. And what about 14 meters per second? Okay, here could be a part C. If the ride malfunctions and does 14 meters per second at the top, is the one, I guess, 14 meters per second at the top. Oh, boy, screwing all everything up. What do we get for the normal force again? Okay, so we're going to use the top. We're going to run through, see what we get for the normal force if that's the case. So I would have a negative. I would have the mass of the rider remaining at 100. But now velocity, I'm going to put 14. 14 squared. Okay, so now it ride malfunctions. It's speeding up. It's getting out of control. The radius never changed. We're still at 20 for the radius. Okay. And now that is equal to, so I'm just grabbing off of the top, we would have the normal force here, and we would have minus mg, which is going to be 100 times 9.8. None of those change. Right? The only thing that changed was that the speed was increased to 14 meters per second. What does that do? All right, so let's figure out what this new value is over here. Right? So we're going to have negative 100 times 14 squared divided by 20. And we get 980. Maybe you saw where this was going. We have negative 980 is equal to the normal force minus 980. So what happens when I add 980 to negative 980? I get a 0. Right? And now my normal force is equal to 0 newtons. What does that mean? What does a normal force of 0 mean? Well, it means that if the ride malfunctions and you're spinning around faster and faster into the circle, when you get to the top, the seat that is holding you down all of a sudden contains no force, right? So this is the effect you get on like a roller coaster when you go down go down a big slope, or you go up and then down a big slope, is that you slightly kind of become weightless. You lift off your seat for that split second, and then you come on back down. That's a normal force of zero. You're experiencing a match in gravity in this force, right? So you'll slightly come off of your seat and come back down, and that'll have a normal force of zero. Nothing's pushing on you anymore. All right, anything faster than that, 14 meters per second, and you're probably going to kind of come flying off of that thing, okay? Because you're going to be, hopefully you got seat belts or something in there, but anything faster than that, you're going to want to start flying off. It also means that when you come down here, if you look at the bottom, it means this number is going to be a lot. Well, this number is going to be 980 if we did it that way. You'd have double the force. 980 plus another 980 to 1960 newtons, right? So the bottom would really be putting the pressure on you, and then you'd come to the top and be weightless, and then get a lot of pressure at the bottom and then back at the top. All right, pretty cool anyway. Hopefully that makes sense. Next time you go to the amusement park, you'll understand the physics behind why your stomach is being played with there on the roller coasters and the other attractions. Okay, we'll start up here with example 4. We're going to move over to the resistive forces. There'll only be a couple of examples on these ones because they're relatively simple. And they don't pop back up until actually physics 2 when you do a little relation to them. So we're not going to worry too much on them, but we are going to do a couple of examples here quickly to get you familiar with what they are. So example 4 here is a bowling ball. It says here we have a 5 kilogram bowling ball. It experiences a resistive force of 8 newtons when traveling at a speed of 4 meters per second through water. Water has a density of 1,000 kilograms per meters cubed. So I'll put the density over there for that given in the problem. So this one has 2 parts. One, it wants us to determine what the resistive constant B is. And for part 2, it wants us to figure out what the terminal velocity is while in the water. Okay. So for the first part, determine the resistive constant B. These ones are usually pretty simple to figure out. We need our resistive equation, which is up here in the corner, or not quite in the corner, the R is equal to BV. You'll notice that it's not in vector form. It depends on what direction things are going. It always opposes the movement of the object, but that's not necessarily always negative. So I've left it up there as R is equal to BV. If we plug in what we know, it tells us in the first line that it is experiencing a resistive force of 8. B is what we are trying to determine. And the velocity at which it is traveling through that is 4. So what is B? Okay, so B is going to just be 8 divided by 4, which should give us 2. So in this case here, what is the constant B? B here would be equal to 2. But what are the units? Okay, I didn't specifically state those. I'm leaving them for you to figure out. In case you get in a bind like this, I want you to be able to work your way through it. I never gave you the units. I don't want you to memorize these things. I want you to be able to solve for them. Okay, so what would we do in this case? Well, B is a force divided by a velocity, right? And the units are given here in the problem, so we should be able to make that work. Resistive force would be newtons. And the velocity that's divided by is meters per second. So this would be meters. And then per second means that the second is going to end up coming up top. So we should have a newton second per meter for our constant. Again, that's fine. It's thinking on the fly, making sure that we know how to work our equations. It tells me that you know your units for the major things. And it works out very well. Okay, we can always find units for these things like this by working back through the equations. Okay, if you get stuck and you can't figure out units, it's a great way of just going back, looking in the problem, getting the ones that you do know and putting them in there. Part 2. What is the terminal velocity while in the water? Okay, for that one, we're going to have to figure out what our terminal velocity equation is. So if we drop a free body diagram, and I have the force of gravity pulling down, that's always equal to mg. and I have this resistive force pulling it opposite of the motion. So in this case, it's pulling it up as this thing travels down through the water. It's in water. Okay. The terminal velocity is reached when these two things equal each other. Okay, they're going to cancel out, which means if we had sum of the forces in the y, we would want them to equal 0. The two forces that are in question would be the resistive force pointing up and the force of gravity pointing down. So force of gravity, I could just write it as m times g. If this is all equal to 0, I can move that mg over to the other side. Mg, it's equal to, and that would be equal to r. What is r? R is b times v. Okay? Because I have put this to 0, this is our terminal velocity. So I can give it a little t down there just to note that that is our terminal velocity. And now I just plug in. What's the mass of the bowling ball? I got to go back to the question and grab that it is 5 kilograms. What is G? That should be burned into your brain by now, that G is going to be 9.8. Equals B. What is B? We just found out it has to be a 2. And then that is times the terminal velocity. Okay. I want you to go ahead and solve out for the terminal velocity. Not hard. We got 5 times 9.8 divided by 2. Okay. Terminal velocity on a bowling ball that travels through water. 24.5 meters per second. Okay. So like I said, these problems are not too difficult. They're not too hard. You do a couple of them and you've pretty much got it. So we'll do one here with the resistive force for a high speed. And that'll probably be where we end this lecture. Okay, so I'll be right back with another example. Yeah, for example 5, I just wanted to show you that you can make up problems, look up answers, stuff like that on your own if you're curious about things and how this works in like real world application things. So for the last one, for the high speed resistive forces, let's look at what is the terminal velocity of an average skydiver, right? How fast are they actually falling when they go skydiving out of a plane? And so for that, I just turned to Google, okay? I look up the average mass of a human. Okay, average mass of a human is around 100 kilograms. I look for the surface area of a human. Okay, how much surface area is in the frontal area of a human. So this would be traveling stomach down towards the earth. And it told me it was 0.7 square meters. So I'm going to go with that. I looked up the density of air. So we're just going to assume it's just regular air and that we're not worried about elevation changes. Density of air is about 1.3 kilograms per meters cubed. And then I looked at what the drag coefficient is of a person falling through air. And it told me it was about 0.74. Okay, so I'm just grabbing these numbers online, just grabbing them from Google, asking AI, and it's just popping up the numbers for me. Let's see if it makes any sense. Okay, so you could do this for anything you wanted, change the mass, change the area, change anything. You could find this out if someone was wondering what terminal velocity is for, any object at any speed. You can go ahead and just put this in. So let's look. Anyway, let's find out what our terminal velocity is for a skydiver. So we do the same principle as we did for the last one, where we look at our sums of our forces in the y. We want that to be 0 for the terminal velocity equation, which means that when we take our skydiver, we have the force of gravity going down, and we're going to have our resistive force pointing up. They'll both cancel out, which means we're going to have R minus Fg, or the force of gravity, which means we end up right back at the same equation that we had in the previous example. Okay, so these aren't too bad. The force of gravity is always going to be m times g. The resistive force in this case, because we are traveling at a higher velocity, we understand skydiving will be at a high velocity. We'll use the R equation for high velocity, 1/2 d rho a v squared. And this is the v now that we're looking for, the terminal velocity equation. Okay, so you plug in some stuff that I know. Our mass here is going to be 100. G is always going to be 9.8. Half is just a nice constant. We'll grab the drag coefficient, 0.74. We'll grab the rho equation, which is, or value, which is 1.3. We'll look at the cross-sectional area, which is going to be 0.7. And then we're left with VT squared. And now we just have to plug all that into our calculators and come up with an answer for terminal velocity. And then we're going to see if it makes any sense. Okay, so if I plug in, this will be 980, so I might as well start with that, 980, and then whatever this value is here, I'm going to have to just divide that over. So 980 divided by whatever that value is, 1/2 times 0.74 times 1.3 times 0.7. If we take all that, we get something around 2911. And this is equal then to VT squared. Okay, so I do need to take a square root on both sides in order to get VT by itself. And this then will give me a terminal velocity of around 54 meters per second. Yeah, something right around 54 meters per second. Now, is 54 meters per second fast? Well, we'd have to do a conversion to figure out what it is in a more relatable terms, like miles per hour. I'll leave that up to you guys. If you want, go back chapter 1, grab your equations, or just hit Google and look for the equations in order to convert that. Of course, Google will convert it for you if you wish, but then you don't learn anything, right? If you do, you go through all the conversions, you'll see that this is roughly equal to 120 miles per hour. So that'll tell you whether or not your conversions are correct. Okay, it's a good idea still to practice those all the way back to chapter 1. 120 miles per hour, yeah, that's pretty quick to be free falling out of a plane in the open air. And you can confirm it with Google or whatever search engine you want. Look up what the terminal velocity is for an average skydiver. And I'm guessing it's going to give you something around 120 miles per hour. Okay. You can change this up. You can change these equations into a lot of different things. You can do the penny example being dropped off of the Empire State Building. Just look up the mass of a penny. Okay, it's going to be very, very small. Its area is also going to be very, very small. You can use the same rho that is traveling through the air, and we'll have to determine what the drag coefficient is of that. All these numbers can just be grabbed. You do a little research, you grab these numbers, you plug in, and you can find terminal velocities for anything, a very wide variety of things. Okay, hopefully that was okay for a good lecture. Like I said, we're going to do a couple of these, but not a lot. So that will conclude Chapter 6 example. Okay, we'll see you in the next chapter.